Hello everyone, welcome back to our live session on discussion of previous year grade question, and this topic is welding connections part 2. Okay, in previous session we have discussed about welding connections part 1. There we have seen some previous year gate questions. Of course, most popular gate questions we have seen number of times repeated models. Okay, whatever we have discussed in previous session, those are the most number of times repeated models in gate. Now here we are going to continue that session. Clear? That means welded connections part 2. Okay. Now, before going into the discussion of these questions, okay, this session, let me announce one thing, that is to get the maximum discount. Okay, to get the maximum discount for the subscription, for the gate subscription in Ekeeda, use this code which I mentioned on the screen, or which I written on the screen. So to get the maximum discount for the gate subscription in Ekeeda, use this code, that is KAURU10, which I mentioned on the screen. Okay. Okay, let me start this session with these questions. So here I have given two questions. Of course, very small questions, but in recent time, these type of models from welded connections have gained popularity. Hence, it is very important to concentrate on these type of models in addition to the models what we have discussed previously. Clear? So once go through these two questions. As I said, in recent times, this type of questions has gained popularity. It means these are the questions. Okay, these were the questions asked in 2018 GATE in session, morning session, and in afternoon session. It means in the very same year, these two questions were asked. Clear? And from then onwards, they keep on asking these type of models. That is the reason I said this particular model has gained popularity in recent time. Once go through this question. Of course, we will discuss the solution for this question in detail, no doubt in that. But go through this question, go through these questions. Two questions here. So once I'll read out these questions. First one, a fillet weld is simultaneously subjected to a factor normal and shear stress of 120 MPa, megapascal, and 50 MPa respectively. Clear? So first, let me write the given informations. So these are the given informations for the first question. The weld used, okay, the weld used for connecting the members is fillet weld. Please make a note of it. As I mentioned earlier, even in our recorded sessions also I mentioned, for connecting the members by making use of weld, we always prefer fillet weld. Okay, we always prefer fillet weld, that is up to 80% we use fillet weld, and rest 15% is butt weld, and remaining 5% is either plug weld or slot weld. So fillet weld is the weld which we use more extensively in our day-to-day life, or in reality we make connections by weld by using fillet weld only. Is that okay? That is the reason all the questions, if you observe the questions what we have discussed in last session, and the questions what we are going to discuss in this session, all those questions are based on fillet weld only. Such an important type of weld it is. The reason why it is asked more widely, because in practicality this is a weld which is used for making the connections, right? Because of that reason only, in examination also these particular weld is asked. Our questions where questions are based on this type of weld only. Fillet weld. Okay. Fillet weld is simultaneously subjected to a factored normal and shear stress. Okay. So normal stress we represent with F. How much? Given in the question 120 MPa, right? And a shear stress. Shear stress we represent with small q. So shear stress given 50 MPa. Okay, shear stress given 50 MPa. These were the given informations. Now he is asking us to find as per IS 800 2007. It means this is the code which we use for carrying out the construction of steel structures. Okay, whether it is industrial buildings or other type of buildings or bridges. So whatever the steel structures we are going to carry out, or we are going to design, or we are going to construct, for carrying out all those steel structures, we make use of this particular code, that is IS 800 2007. Very important. Okay, so now he is asking us to find as per that IS 800 2007. And one more thing, in this IS 800 2007, it was mentioned about limit state method. Okay, about the limit state method in this code it was mentioned, right? So now as per that code, he is asking us to find the equivalent stress. Okay, now equivalent stress. Equivalent stress. This is what he is asking us to find. Okay, as I said, these were the given informations in the question. That is, in question it was mentioned about normal stress and shear stress. Of course, they are factored. Okay, factored normal stress and factored shear stress. Now he is asking us to find equivalent stress as per IS 800 2007. And before going into the answer, okay, before going into the discussion of the answer for this particular question, I want to make one thing very clear. That is, if you go through the various previous year gate books in the market, we will find multiple answers for this question. Okay, for this question we'll find multiple answers in various previous year gate books what are going to available in market. Hence here I'm going to explain the answer, okay, or solution. Okay, here I'm going to explain the procedure to get the answer which exactly matches with the key given by the concerned IIT which conducted the examination that year. As I said, these two are the previous year gate questions in 2018. Okay, these two were the previous year gate questions in 2018. Sorry, not 1918. And if you see various books, there exist multiple answers. Okay, multiple answers. But the procedure what we are going to discuss here, by that procedure we are going to get a correct answer which matches with the key or answer given by the concerned IIT which conducted that exam. Okay, which conducted that year examination. Okay, and for that, okay, to get the correct answer which matches with that IIT key, one need to have the knowledge about the provisions mentioned in the code IS 800 2007. So first let me explain about that clause or provisions mentioned in that code, and after we will go for answer. It means if we are aware of that provision, then within a one line we can answer this question. Okay, if you are having the knowledge, okay, if you are aware of that provisions or clauses corresponding to this particular case, then we can answer this question in one line, right? That is the reason this question is asked for 1 mark. Okay, as I said, these two questions are from 2018 gate, so each 1 mark. So what is that question, what is that class here? I will mention here. So here I am mentioning that class as per IS 800 2007 class. Class 10.5.10.1.1. Okay, this was the class in which this equivalent stress was mentioned. Okay, this was the class, once I repeat, 10.5.10.1.1. This was the class in which the equivalent stress was mentioned, or formula for this equivalent stress was mentioned. That is, equivalent stress Fe is equal to under root F square plus 3Q square. Okay, this was the formula mentioned in that class. Clear? As I said, if we are aware or if we are having the knowledge of this class, then as I said, we can answer this question within one line. Hence, this question is for 1 mark. Clear? And one more provision is there, or one more condition is also, okay, one more condition also mentioned in this class, that is, FE equivalent stress should be less than or equal to design stress, that is FU by root 3 into gamma MW. As we know about this gamma MW, so this gamma MW is the factor of safety for weld material. Okay, factor of safety for the weld material, and that factor of safety is equal to 1.25 if that welding is done in workshop. So simply here I will write as shop, and 1.5 if that weld is done in field. Okay, so this is about that class. It means for solving this question, one need to have the knowledge about this provision. This is the provision and the class. Okay, class in which this provision was mentioned is 10.5.10.1.1 in IS 800 2007. Is that clear, everyone? Now, as I said, based on this, we can solve this question very easily. So, as in the question, it was very clearly mentioned normal stress and shear stress. Now, is asking us to find equivalent stress. Now, equivalent stress Fe is equal to equivalent stress Fe is equal to, as it was mentioned, normal stress as a 120 MPa and shear stress as a 50 MPa. So, under root normal stress 120 square plus 3 into shear stress 50 square. Okay, upon solving we are going to get answer as a 147.98 MPa. This was the answer. Okay, this was the answer for the first question. So see the first question. Once again, I'll repeat this question. A fillet weld is simultaneously subjected to factor normal and shear stress of 120 MPa and 50 MPa respectively. As per IS 800 2007, the equivalent stress in MPa up to 2 decimals is. So the answer for this question 147.98 MPa. Clear? Now let us go for the second question. Second one. Same as we know all the things. Okay, as we have discussed all the required things to solve this question. And second question, I'll write the final step, or directly I'll write the step which is required to get the answer. Okay, no, I will not repeat again all these things, the provisions and everything. So required things are already on the screen. If you want, you can copy this. Okay, required things to solve this question are on the screen, so you can copy this. So here for this second question, directly I'll write the step to get the answer. So equivalent stress Fe. So first let me write the given informations in that question. So see the second question. In a fillet weld, the direct shear stress and bending stress are 50 MPa and 150 MPa respectively. As per IS 800 2007, the equivalent stress will be. Okay, that is what is asking. Now the shear stress, how much the shear stress? Direct shear stress 50 MPa and bending tensile stress are 150 MPa. Now is given in this question shear stress Q as 50 MPa and normal stress F as 150 MPa, right? Now is asking us to find King Khan. Yeah, hello. Okay, so first concentrate here. The equivalent stress Fe. We know that under root F square plus 3Q square, right? So Fe is 150 whole square, 3 into Q is 50 square. Okay, upon solving we are going to get answer as 173.21 MPa. So this was the answer. As I said, within one line we can answer this question if we are aware of this provision. Once I will repeat that provision. What is that provision? Clause 10.5.10.1.1. In this class, these provisions were mentioned. So those provisions already have mentioned on the screen. Okay, already they are on the screen. So once go copy this provisions and we can solve this answer easily, or we can get this answer, or we can solve this question very easily. Is that okay? So this is the solution for these two questions asked in the 2018 GATE. Very easy. But as I said, this particular type of model as gaining popularity in recent time. Okay. If it is completed, then I'll go to the next question. So these are the two questions which are on the screen. And answers for that question are already discussed. Okay. Now I'll proceed to the next question. This is the next question which was asked in 2019 GATE. Once go through this question and go through the diagram also. And again, for solving this question also, we require the provision what we have discussed previously. That is equivalent stress. Fe is equal to under root F square plus 3Q square. We should be less than or equal to the design stress in weld. That is Fu by mainly the design stress in fillet weld. That is Fu by under root 3 into gamma MW. Clear? That was the provision. Now this question is also based on the same provision. And the concepts required to solve this question were already discussed or are already covered in our recorded sessions. Okay, in our recorded sessions of our steel structures, everything was covered clearly, right? Let's go through this question. Okay, I'll read out this question. A 16 mm thick gusset plate is connected to 12 mm thick flange plate of an I section using fillet weld on both sides as shown in the figure. So if you observe here, this was the gusset plate. Okay, it was very clearly mentioned. So if you observe here, this is the gusset plate, right? This is a gusset plate having a thickness of 16 mm. Okay, this gusset plate having a thickness of 16 mm is connected to a 12 mm thick flange plate of an I section. So this is the flange. Okay, this is the flange plate which was mentioned in the diagram given in the question, and the thickness is 12 mm. So the flange, okay, this is the flange and this is the gusset plate. Both are connected by making use of fillet weld. So see here, fillet weld. So this is the fillet weld, the shaded part. Okay, the dark shaded part. Here I am again shading with red color on the screen. Try to observe. Okay, now these two are connected by making use of fillet weld. Okay, this is the front view and the side view is also mentioned. In side view, we can observe the cross section. Okay, in side view, we can observe the cross section of the fillet weld. It means see fillet welds are present on both sides of the gusset plate. So here, this is the I section. Here, this is the I section. Okay, here, this is the I section and this is the gusset plate. And as mentioned in the question, these two are the fillet weld. Okay, these two are the fillet weld present on either side of that gusset plate. Clear? And the length of that fillet weld mentioned as a 500 mm. So this is considered as the length of the weld. We can represent with L effect or LW. Clear? Let us proceed to the question. Okay, let us continue the question. Now the gusset plate is subjected to a point load of 350 kilonewtons. See here, 350 kilonewtons. Here it is, acting at a distance of 100 mm from the flange plate. So this can be considered as the eccentricity E. So how much E? 100 mm mentioned in the question. Clear? 100 mm from the flange plate. Size of the fillet weld. So size, yes, we represent size with S. So how much the size? 10 mm mentioned in the question. So these are the given informations. Once again I read the question. Okay, once again I'll read out the question. A 16 mm thick gusset plate is connected to the 12 mm thick flange plate of an I section using fillet weld on both sides as shown in the figure. The gusset plate is subjected to a point load of 350 kilonewton acting at a distance of 100 mm from the flange plate. Size of the fillet weld is 10 mm. These are the given informations, and of course we have seen the diagrams also. So this is the front view and this is the side view. Now he is asking us to find, maximum resultant stress. So here see, maximum resultant stress is nothing but equivalent stress. He is asking us to find equivalent stress. Okay. Maximum resultant stress in MPa, round off to 1 decimal place on fillet weld along the vertical plane would be. It means simply is asking us to find the equivalent stress for the given question or for the given diagram or for the given welded connection simply. Is that okay? As I said, for solving this question, one need to have the knowledge of the provisions what we have discussed previously. So once I will write that provision here. Equivalent stress Fe is equal to under root F square plus 3Q square. Clear? As I said, once again I'll write the class here. 10.5.10.1.1. This was the class in IS 800 2007 in which this particular provision was present. Is that okay? So here for solving the question, one need to have the knowledge of this provision. Okay, one need to have the knowledge of this formula or provision. As I said, in recent time, this particular model has gained popularity. It means previously what we have discussed, those are the questions. Okay, those were the questions in 2018 GATE, and this was the question in 2019 GATE. That is the reason I said in recent time this model became more important. Okay, once I can go through the question and we'll start the discussion. Okay, we'll start the discussion for the solution. Okay, we start the discussion for the solution of this question. Now, if you observe the previous questions and this question, in previous question, normal stress and shear stress were mentioned, and that those questions are for 1 mark. But here, in this question, nothing was mentioned, but the information regarding the connection was given. Okay, information regarding the connection was given. Hence, we need to find the normal stress and shear stress, and finally, by making use of those normal and shear stresses, we have to find the equivalent stress. There where we are going to get the answer. Is that clear? And one more thing I want to make it very clear. This particular type of welding comes under which category? Of course, in our discussion part or in our recorded sessions, we have discussed about some types of eccentric welded connections, right? That is type 1 and type 2. Now, this particular type of welding comes under type 2. Okay, this particular type of welding comes under type 2. So, briefly, I'll revise the concepts of the type 2 weld. Okay, briefly I'll revise here the concepts of type 2 weld, and later we'll see the solution for it. So type 2 weld. Type 2 means out of plane eccentricity. Out of plane eccentricity welded connection. Okay. For that, one need to have the cross section of the fillet weld. Okay, see here. Here inside view we can observe the cross section of the fillet weld. It means here we can see the throat thickness TT and of course the length of the fillet weld. So those two fillet welds I am going to combine and I am going to show the cross-sectional view of the fillet weld. So here I will draw the cross-sectional view of the fillet weld. Okay, these are the two welds which are present on either side of the gusset plate. So this is the weld present on one side and this is the weld present on other side. And if you see the axis, so this is one axis, let us take it as XX, and this is one more axis, that is vertical axis YY, right? Okay, this is a cross sectional view of fillet weld, cross section of fillet weld. Cross section view of fillet weld. And if we show the dimensions, this is the total width, right, which is TT, and this is the length, LW. Is that okay? So in the question it was mentioned length of the weld LW as 500 mm, and for getting the throat thickness we know that KS formula mentioned the code. So here K is 0.7 and S is 10, which was mentioned. See here. Here this was the size. Okay, size of the fillet weld 10 mm and length of the fillet weld here it was mentioned 500 mm. That is what I have written here. So how much it is the throat thickness? 7 mm. It means the total width of the fillet weld is 2 TT, that is 2 into 7, that is 14 mm. These are the cross sectional dimensions of the fillet weld. Okay, this is the cross sectional. Okay, these are the cross sectional dimensions of the fillet weld, and this is the cross section of the fillet weld. And this weld is comes under type 2, that is out of plane eccentric weld. Okay, out of plane eccentric weld, and this out of plane eccentric weld is subjected to. So come on, try to answer this. So out of plane eccentric weld is connected to two stresses. Okay, two stresses or two effects. That is, one is direct shear stress. As I said, everything was discussed in our recorded sessions. Here I am briefly revising that. Direct shear stress, which we represent with Q. So to get the direct shear stress, the formula is nothing but force on that weld or force applied by area of the weld. Okay, so force we represent with P and area of the weld. Area. Is that okay? Now how much the force? 350 kilonewton, that is 10 cube upon area. So area is nothing but 14 into 500. Now how much the value we are going to get? 50 MPa. So the shear stress, okay, the direct shear stress onto this weld. So this is the weld, the direct shear stress onto the weld because of out of plane eccentric load. So this is out of plane eccentric load. So this 350 is out of plane eccentric load. Because of this 350 out of plane eccentric load, this particular weld group is subjected to direct shear stress and normal stress, that is bending stress. So the direct shear stress formula is load upon area of the weld, and the other effect because of this out of plane eccentric weld is bending stress. Bending, of course, bending stress is a normal stress, no doubt in that. Normal bending stress, hence I will write it as normal bending stress. Okay, so normal bending stress we represent with F. As we know the formula the formula what we use, okay, the formula what we use to calculate the normal bending stress is nothing but the formula what we have studied in strength of materials in topic pure bending. Okay, in simple theory of bending, okay, in simple theory of bending, whatever the formula we have studied, the very same formula we are going to use here to get this bending stress. Clear? What is that formula? Most popular formula, most known formula, that is m upon I is equal to, here I will write in bracket, I will write the most famous formula what we have studied in strength of materials in simple bending theory concept. So m upon I is equal to F upon Y is equal to E upon R. Now here we are going to use the first two terms. Here we are going to use the first two terms. So upon using the first two terms, we will get stress, bending normal stress as F is equal to m upon I into Y. Is that clear? Okay. Now M is nothing but the load into eccentricity. So here in bracket I will mention the given things. The moment, M is the moment, which is nothing but load into eccentricity, which is 350 into 10 cube. The eccentricity, how much it was given? Eccentricity given as 100 mm. Okay, this was the eccentricity. Okay, this was the distance between the CG of the weld group and the load. Okay, line of action of the load. That is 100 mm mentioned in the question. So 100. Clear? Now, moment of inertia I. So here bending will occur along x-axis. Simply write I. But strictly speaking, it is I-axis. So moment of inertia along the bending axis, that is along this x-axis axis, is nothing but BD cube by 12. So here B is nothing but 14 and D is nothing but length of the weld 500 mm. So here moment of inertia is nothing but 14 into 14 is D is nothing but 500 whole cube upon 12, and Y, distance of the extreme fiber from neutral axis, that is 250 mm. So total, okay, here the total length, or you can say total depth, is length of the weld or depth of this cross section is 500 mm. Now from the neutral axis, so here x-axis itself is the neutral axis, here I will mention. So x-axis itself is the neutral axis. Now Y is the distance of the extreme fiber from this neutral axis. Obviously this is the Y, right? (250 mm). Is it clear? These are the given parameters in that formula, and that formula is from simple bending theory, right? Now let us substitute all these values here to get the normal stress. To get the normal stress, substitute all the values. So moment, so here I will write moment is nothing but 350 into 10 cube into 100, and Y is nothing but 250 divided by moment of inertia, how much it is? 14 into 500 whole cube, and this 12 comes on to the numerator into 12. Clear? So 350 into 10 cube into 100 into 250 into 12 upon 14 into 500 cube. Upon simplifying, we are going to get it as 60 MPa. So now we have calculated the direct shear stress and normal bending stress. Upon getting these two values, we make use of this particular provision or this particular formula mentioned in the code, that is F square, that is equivalent or resultant stress is equal to under root F square plus 3Q square. Clear? Come and do it. So now Fe. Here normal stress is 60 square. So shear is 50, 3 into 50 square under root. So finally we are going to get it as 105.35 MPa. This was the answer for this question. How much? 105.35 MPa. Once again, I will show from the beginning. See here. This was the question. Okay, once again, I'll read out the question. A 16 mm thick gusset plate. Okay, first you go through it. After that, I'll repeat the reason. This is somewhat the typical model, and in recent times, this model has gained popularity, or more weightage was given to this type of models in recent times GATE question. Okay, in recent time GATE examination, from this subject, that is design of steel structure, this particular model was asking. Okay, the gate, in a gate examination we can observe this type of question. And once you go through it, and later once again I'll repeat it. Okay, later I'll repeat this particular solution. Okay, once go through it. And this was the question, and this is the provision. Okay, this is the provision we need to use to get the solution. Okay, which was mentioned in IS 800 2007 clause 10.5.10.1.1. Okay, and this particular type of welding comes under type 2 category, what we have discussed in our recorded sessions, that is out of plane eccentric welded connection, and this is the cross section of the fillet weld, as the fillet weld is done on either side of the gusset plate, and those two welds are shown here. And the width here is 2 times the throat thickness, that is 2 into 7, 14 mm, and throat thickness formula is K constant into S, that is size of the weld, which is 7 mm. Finally, we are going to get throat thickness as 7 mm, and width of this fillet weld is 14 mm, and length or depth of the cross section of the fillet weld is 500 mm mentioned in the question. And this out of plane eccentric welded connection is subjected to two types of effects or two types of stresses. One is direct shear stress, which is Q, which we represent with Q, is equal to P upon area, that is a load 350 kilonewton, that is 350 into 10 cube by area 14 into 500, which comes out to be 50 MPa. And one more type of effect onto this weld group because of this out of plane eccentric load is normal bending stress F. So to calculate this normal bending stress, we are going to make use of the famous formula what we have studied in strength of materials in simple bending theory, right? That is M upon I is equal to F upon Y is equal to E upon R. Now here in this question or in this welded connections, we are going to make use these two terms. Okay, we are going to make use these two terms to calculate this stress F. Now F is equal to M upon I into Y, right? Now M is nothing but moment. To get the moment, okay, to get the moment, we need to multiply the load and the distance between weld group. Okay, distance between weld group and the line of action of the force, that is PE. So load is nothing but 350 into 10 cube, that is kilonewton, and the eccentricity is 100 mm, that is the moment. And moment of inertia I. So here I we need to take about the bending axis. Undoubtedly the bending will occur along this x-axis, which is the neutral axis here. So moment of inertia about that x-axis is nothing but BD cube by 12. So here B for the cross section, B here is 14 and D here is LW, which is 500 mm. So here 14 into 500 cube by 12. That is the moment of inertia. And Y is the distance of the extreme fiber from the neutral axis. Okay, distance of the extreme fiber from the neutral axis. So neutral axis is x and the distance of the extreme fiber, this is 250. So everything is here. Upon substituting these values in this formula, we are going to get normal stress as 60 MPa. By making use of this F and Q, finally we will get the resultant stress, that is Fe is equal to under root 60 square into 3 into 50 square, which is 105.35 MPa, right? Once go through this. So from the cross section of the fillet weld, I will show here. Okay, so very important model. As I said, in recent time, this particular model Okay, this particular model has gained popularity, or you can say the particular IITs which are setting the paper every year are focusing, are they are giving more weightage to this type of model from welded connections. Okay, very important. Now let us go to the next question. So this was the question in 2020. Okay, in 2020 this was the question. Let's go through this question. And one more thing, for solving this question, okay, for solving the question which was asked, or which the for solving this question which was on the screen, which is asked into the which was asked in 2020 gate. Okay, for solving this question, one need to have the knowledge of strength of materials concept, that is shear stress formula in beams. Okay, what is that shear stress formula? Here I will write that shear stress formula. As I said, for solving the question on the screen, okay, for solving the question on the screen, which was the question, okay, which was the question asked in 2020 gate, okay, which was the question asked in 2020 gate. So Q, one need to have the knowledge of the formula for shear stress studied in 2020 gate, that is Q, shear stress in beams, is equal to FA pi bar upon IB. So first let me explain each and every term in this formula. Okay, first let me explain each and every term in this formula. If you are aware of each and every term in this formula, then we can solve this question very easily. Okay, that is why I keep on saying all the time, if we have the perfect knowledge of strength of material concepts, then we can learn and answer the questions from these steel structures very easily. That is the key point here. Okay, the key point in mastering these steel structures and getting all the marks, okay, getting all the marks from the questions on this subject is having the knowledge of strength of materials. As I said, for solving this question on the screen, which was the 2020 gate question for 2 marks, okay, 2020 gate question for 2 marks, one need to have the knowledge of shear stress formula for beams studied in strength of materials. That was the formula was Q is shear stress Q is equal to FA y bar upon I into B. Clear? So first let me explain the terms here, and later we go for the question. Okay, later we'll study this question, and after that we'll see the solution also. Shear Q, as we know, Q is nothing but shear stress. Okay, Q is nothing but shear stress. F is nothing but shear force. Now A y bar. So this is the tricky term in this formula. A y bar is moment of area. Okay, moment of area of area above the level where shear stress is required. Where shear stress is required. Okay, as I said, this particular term is somewhat tricky in this formula. Okay, so A y bar is a moment of area above the level where shear stress is required. So I'll explain it with rectangular cross section. Okay, rectangular cross section is quite easy to understand. So here I'll take a rectangular cross section as an example. So this is the cross section, rectangular cross section, and here where the neutral axis will be there. Okay, here where neutral axis will be there. Okay, now if I want to calculate shear stress at this level, now at this cross section xx I want shear stress. It means at this qx I want the shear stress at this level. Now for getting the shear stress at this level, we need to find the moment of area. Okay, moment of area above the level. So here this is the level. Okay, x-axis is the level. Now for this area we need to find the moment. Okay, for this area we need to find the moment about the neutral axis. It means this is a neutral axis and this is y bar, and this was the area A. Is that clear? So once again I repeat. So AY bar is the moment of area. Okay, AY bar is the moment of area above the level where shear stress is required. Okay, moment of area above the level. So this is the level. Now the area above the level is this one, shaded part. Okay, shaded part is the area above the level where shear stress is required. That is what AY bar. Okay, that is what AY bar. Somewhat tricky term in this formula. Now rest of the terms are clear to us. Okay, rest of the terms are clear to us. I is equal to moment of inertia. Moment of inertia about neutral axis. Undoubtedly it is about neutral axis, right? Now B is equal to width of cross section. Clear? So these are the terms. Once go through these terms. As I said, this was the formula. Okay, here once I'll write or I'll mention that formula. This formula as already studied in strength of materials. Okay, this particular formula Q is nothing but shear stress in the beams. So Q is equal to FA y bar upon IB. So this was the formula studied in strength of materials. So one need to have the knowledge of this formula to solve the question for 2 marks. Okay, question for 2 marks asked in 2020 GATE, right? So the terms here, Q is nothing but shear stress at a particular level and F is nothing but shear force at the cross section. Okay, shear force at the cross section which is causing the shear stress Q, and AY bar. So this is what somewhat tricky term here in this formula. That is A is nothing but moment of area about a level. Okay, about a level above area above the level. Okay, area above the level where shear stress is required. Okay, moment of moment of inertia of area, moment of inertia of area above the level where shear stress is required. Now here in this example, so with this rectangular cross section, I have explained what is AI bar. So AI bar is nothing but AY bar. Okay, AY bar is nothing but. So here we have considered XX as a level. At this level we want shear stress which is QX. Now to get this shear stress QX in this formula AY bar is nothing but the area above this level is the shaded part and Y bar is nothing but the distance of the CG of this area from neutral axis. So multiplying those two A and Y bar, we are going to get AY bar in this formula, and I is nothing but moment of inertia about neutral axis, and B is the width of the cross section. Is that clear? These are the given things. Sorry, these are the required things. Now let us go through this question. So this was the question. See here, question is on the screen. Let's go through this question, and I'll read out this question also. A flange and web plates of a doubly symmetric build-up section are connected by continuous shear flange. So these two are the flange plates. Okay, this is the flange. This is also flange. These two flanges. Okay, so these two flange plates are connected to web. So these two are the web plates. Clear? These two are the web plates. Here I will write. These are the web plates, and this one and this one are flange plates. These are the flange plates. So now flange plates and web plates of a doubly symmetric build-up section. So this is the diagram shown on the screen is doubly symmetric build-up section. Now for getting this doubly symmetric build-up section, we have used two flange plates and two web plates, and those web plates and flange plates are connected by making use of fillet weld. See here, 10 mm thick fillet weld. Okay, now what is the size of fillet weld? Here I will write. So 10 mm size fillet weld. So fillet weld as shown in the figure. Now moment of inertia of the section about XX. So see here XX is nothing but neutral axis here. For this section here this is XX which was mentioned clearly. Now this XX itself is the neutral axis. Clear? XX. So it means I already given. So see here this was the I was mentioned in the question. I is equal to how much? 7.73 into 10 to the power 6 mm power 4. Okay, 7.73 into 10 to the power 6 mm power 4. Clear? Got the moment of inertia. Now permissible shear stress in the fillet weld. So permissible shear stress we represent with QP. How much here I'll write? QP. QP is equal to 100 Newton per mm square, or it is simply MPa. 100 MPa. Is it clear? The design shear strength of section is governed by the capacity of the fillet weld. It means the fillet weld is always failed by shear, right? Fillet weld is always failed by shear. Okay. Now what is asking? The maximum shear force in kilonewton that can be carried out by the section. It means in this formula he is asking us to find F. Is asking us to find F, and of course Q was mentioned, that is QP, and we need to find AY bar, and of course QI moment of inertia was also mentioned, and Q is also mentioned, and here we need to find AY bar, that is a moment of area above the level at which shear stress is to be calculated. Okay, shear stress is to be calculated, and B is the width. So these two terms we need to calculate to get the answer for this question. That is A y bar and B, right? Now let us write this formula. So now Q, once again I'll write this formula. Q is equal to F A y bar upon IB. Okay. From this we need to find F. It means Q into IB upon A y bar. Is that okay? Now given. So first let me write the given informations. Q. So Q here is nothing but QP, how much? 100 MPa or Newton per mm square. And I is how much? 7.73 into 10 to the power 6 mm power 4. Okay. Now B. So here B is nothing but we have to take the cross section, or we have to take the width in which the failure is taking place. So in the question it was mentioned that see this line, the design shear strength of the section is governed by capacity of the fillet weld. Hence here we have to take a cross section of a fillet weld at which failure will occur. And one more thing, the fillet weld always fails by shear, and the cross section of fillet weld which fails in shear is nothing but the throat thickness, or throat, okay, throat TT into length of the weld. So obviously here we need to take width as a throat thickness, and here how many welds are present? So for each web the fillet weld is present on either side, and here two web plates are there, hence obviously four fillet welds are there. Okay, for each fillet weld the throat thickness is nothing but, okay, for each, here I'll write, for each fillet weld the throat thickness is nothing but KS, which is nothing but 0.7 into 10, that is 7 mm, right? That is 7 mm. Now here width at which the failure is taking place is nothing but 4 into TT, which is nothing but 4 into 7, directly I will write 28 mm. Now AY bar. So AY bar is nothing but, here we need to find the shear stress at the location of the weld. So here where the weld is present, right? Here where the weld is present. Here where the weld is present. See the diagram which is on the screen. Now here where the weld is present. Now AY bar is nothing but moment of area of the area above the level at which shear stress is to be calculated. Now area above this level is, this is the area above the level. I'll shade here. I'll shade that area. Is that okay? Now what is that area? That area is nothing but area of the flange plate. Area of the top flange plate. How much it is? 100 into 10. So area of the top flange plate here is A. 100 into 10. That is 1000 mm square. Now y bar is nothing but distance of that area from neutral axis. Okay, distance of the CG of that area from the neutral axis. Now if you observe here where the CG will present, right? Now here where the neutral axis is present. So upon simple mathematics we are going to get this y bar as 55. So y bar as 55. It means see the total is 120, right? So total is 120. If we subtract this 10, okay, and this 10 from this 120, we are going to get 100. It means up to here this is 50. So from neutral axis to here the distance is 50. This is 50. Now the CG of this CG of this flange plate is 5 mm. So 50 plus 5 it is 55. Simple mathematics. So y bar is how much? 55. Y bar is 55 mm. Now a y bar is nothing but 1000 into 55 mm cube. Now everything, okay, every term in this formula is known to us to get the shear force. So now F is equal to Q. Q is how much? 100. And the moment of inertia is nothing but 7.73 into 10 to the power 6 into width is nothing but 28 divided by AY bar. AY bar is nothing but 1000 into 55. So upon simplifying this calculation, we are going to get the answer, that is 393.53 MPa. So this was the answer for this question. As I said, to solve this question, one need to have the knowledge of the shear stress formula studied in strength of materials. Okay, shear stress in the beams formula. Okay, shear stress in the beams formula studied in strength of materials. That is Q is equal to F A Y bar by IB. Hence, one need to have the knowledge of this formula and even the knowledge of the each and every term present in that formula. Then we can solve this question. Of course, little bit steps are involved. Okay, we can't get this answer. Okay, we can't get the answer for this question directly, and this question is for 2 marks, which was asked in 2020 GATE question. Okay, 2020 GATE examination. So see this, these are the given informations. So here we have calculated A, Y bar and B. These are the two things to be calculated. Okay, these are the two things to be calculated, that is A, Y bar and B, to get this answer or to get the maximum shear force. So finally answer is 393.53 MPa. Is that okay? Once go through this. So if you have any doubts, you can ask. So these are the total previous year GATE questions from this topic, welded connections. Okay, from the welded connections, whatever the questions we have discussed in previous session and in this session are only the questions from previous year GATE. So whatever the questions we have discussed from welded connections in last session and in this session are only the previous year GATE questions, and which we have covered in detail. So total I guess some 6 questions. Okay, not 6 questions. Total 7 questions we have covered. Okay, total 7 questions we have covered. So all those 7 questions are from previous year GATE questions. And once again I'll repeat, to get the 2 to 5 marks or 2 to 6 marks from these steel structures, one need to have the knowledge of, or one need to have the perfection on plastic analysis topic, and after that bolted connections and welded connections. From these 3 topics we can easily score 2 to 5 marks, which will give us leading edge. Okay, and before closing this session, one small thing I want to mention, that is to get the maximum discount for GATE subscription in Ekeeda, use this code. That is, here I will mention KAVURU Kauru 10. So use this code. Okay, use this code to get the maximum discount for GATE subscription in Ekeeda. Okay. Now with this I am going to close this session. Thank you.